transformation part, I have given you a homework question. You're required to do that before you come to the lab so that we can simulate it. Now let's move on to applying this so that we can define a manipulator structure. Now, if you look at the transformation matrix, H4x4 homogeneous transform, we said that it is R, B, 0, 1. This is R3x3. Right? So you can encompass both a rotation and a translation within a single matrix. This is really important because when you look at a manipulator, let's take a very simple manipulator. Let's say this is only 1 degree of freedom. This is T, right? As this moves here, if this is O1 and this is O2, right? You have one frame here, which is X0 and Y0. Here you have another frame, X1 and Y1. Okay. Now what is happening is, as this is rotating, the rotation matrix will change. And also D should change because as this moves, the coordinates of this point, x comma y comma z, will change. So this will also change, right? So we need to define a structure such that as the manipulator moves, I can track the coordinates of the end effector, okay? And we'll use that, we'll try to do it using the H matrix because we can have both rotation as well as translation and encompassed into it. So we start with defining a manipulator structure. Now, when you have to define a manipulator structure, it is a definition of how links are arranged. For example, you could have links, let's say they are arranged perpendicularly, but perpendicular does not specify everything in 3D space. It could be any one of these angles, or it could be just an offset in a direction that unless specified you cannot tell what it is. So we use a notation, a mechanical notation, which is known as Denevitt-Hattenberg notation. Or we simply call it the DH notation. Okay. A DH notation is simply a way of representing a manipulator structure. Now, this will tell you how to write down representing is manipulator Now, we need an X number of parameters or N number of parameters to define a manipulator. The way that this notation works is that it is reduced into every link can be defined by 4 independent parameters. So the minimum number of parameters that you need to define any manipulator link is 4. So we'll need 4 parameters to define every manipulator link. So we need 4 parameters. The reason we need 4 parameters is because we want to build a transform for a link. So for example, we have the 4 parameters are A, alpha, D, C. Okay. A, alpha, and D, theta. Every link is defined by 4 parameters. A is your link length. Okay. A is known as the link length. Alpha is link twist or joint twist. Okay. D is your offset, link offset. or joint offset, and theta is the joint displacement.
Professor, four parameters to define what?
To define every manipulated link. To define every manipulated link. Now when you have a revolute link, let's say I have a revolute link. In the case of a revolute link, I have a theta is variable. So this will be variable. In the case of a joint displacement, theta is a variable parameter. Okay. When you talk about a prismatic joint is, let's say I have a joint like this, right? And then you have a joint which is moving in this direction, D. So this is your joint displacement, right? So in this case, D is variable. This is a linear displacement, so in this case, joint link offset, or this will be variable, okay, parameter. In the case of it, this is in the case of a prismatic joint. This is in the case of a revolute joint. Okay. So we'll go on defining these four parameters for every link that we have. So for example, if I have a 3 degree of freedom manipulator, I'll write a table like this. A, alpha, B, theta. Every link will have one row. So this is link 1, link 2, link 3. Okay. So in the case of a RPP manipulator, let's say. Now if all of them are constant, that means it's a rigid link. You cannot have a rigid link. I mean, there is no motion associated with it if the link is rigid. So if theta is not variable, if theta becomes constant, then this link is fixed. Let's say theta is constant at 30 degrees. Then there is no motion, right? It's fixed. Okay, it's not moving. So you have to have, in some cases it might be a rigid link, that's okay. But at least one of the parameters in this, either D or theta. If D is variable, that means it's a prismatic joint. If theta is variable, it means it's a revolute joint. So when you have RPP, you have 3 variables. So R is revolute, so we write it as theta 1. When we put a star, it means it's a variable parameter. P, that means D2 is variable, and D3 is variable, because these are prismatic joints. Everything else will be a constant. Okay? Everything else will be a constant. So if it was RRR, theta 1, theta 2, theta 3 are variable joints. Okay? Anything that is variable will represent it by an asterisk, so as to say that these are variable parameters, right? So eventually we need to know how to find out the 4 for a given structure, all right? So we need to know how to find out A alpha, B theta for a given structure. So how do we do this? So let's say that we have 2 links, right? So we have a simple structure. Let me draw this and then we'll go ahead with it. So let's say this is origin 1, origin 0. Now there are a few steps that we have to follow as we go along to set up a set of frames and references and origins so that we can set up a pH table. Okay. Now one thing that you have to remember is whenever you construct a frame, the way you choose your axis is we use a right-hand frame of reference. Right-hand reference frame. What is a right-hand reference frame? Right-hand reference frame is, as opposed to these fingers representing the axis, you'll have your right hand, 3 fingers represent the axis, your thumb is your Z, index finger is your x-axis, and the middle finger is Y. So your thumb will be your Z-axis, index finger is your x-axis, and middle finger is Y. Okay. So if you point the axis, you'll have the axis represented like this. So Y is within the board, Z is the thumb, and X is along the plane of the board. Okay. So that is how you will represent the axis. Now, make sure that if you use your left hand, that the axes are wrong. All right. So the first thing that we do when we have a given man planar is the first step is to set up the Z-axis. Okay. Step 1 is to set up the Z-axis. Now the way we set up the Z-axis is, if it's a revolute link, or revolute joint, Z is about the axis of rotation. And if it's a prismatic link, Z is along the axis of this place. Okay. So let me give you an example. We'll just take a revolute case in the first case, and then we'll move on to more complex examples. Let's say I have a 2-degree of freedom man planar. So the link length here is A1, this is A2. Okay, so the first thing that I do is, obviously this is going to be So the first step for me here is to have the Z-axis set up. Now, one thing that you have to remember is the Y-axis is not of much importance in the case of a pH table. So even if you don't draw it, it's okay, but it's always a good practice to complete the frames and have the Y-axis. But for the beginning, just so that we are not confused and we are not going to be using Y in any of our measurements, so I'm just going to avoid drawing this, but as we proceed, we'll try to complete all the frames. Okay, so let's say these are the standard axes. This is where the reference is, and this is going to be O0, O0, and that's X and Y. Now, because these two joints are revolute, the axis will be perpendicular to the axis of rotation. So this is about this axis, so this is going to be Z0 and Z1. Okay, this is perpendicular to the board, Z0 and Z1. The next thing we have to do is set up the x-axis, because we are not going to bother much about the y-axis. Okay. Now to set up the x-axis, the first thing is we have to go about setting up the origin. Okay, because it's really important how you set up the origin. To set up the origin, we have to take the two z-axes together. Now there are different cases. Let me explain here. When you have two z-axes that are perpendicular, like so, in this case, let's say this is zi and this is zi minus 1. Okay, this is case A. Then you can have the origin where zi is intersecting zi intersects zi minus 1. So you can have the origin, locate the origin, at the point of intersection. Okay, which is not the case here. Okay. Now, the other case is both of them are parallel. So B, Zi and Zi minus 1 are parallel like this. In this case, you will take the origin where a common normal is intersecting both of them. So for example, in this case, you draw a common normal. A common normal will intersect Z and Z1. A common normal to this is either like in this direction or in this direction. So a common normal will intersect here. So what I'll do is I'll have my origin here, like this, O1. Okay, so locate the origin. Where a common normal to both Zi and Zi minus 1 intersects Zi. Okay, so I have placed, so in this case it will be at this point, right? This is a common normal, or it would have the common normal can be in this direction also, it doesn't matter. So this is the point of intersection, I'm sorry, Zi and Zi minus 1. So this is the point of intersection, so you will have OI here. The other case is like this, where both of them are, this is perpendicular, Zi is perpendicular to Zi minus 1, here Zi is parallel to Zi minus 1. The third case is where both of them are collinear, so Zi minus 1, they are like this, okay, they are in the same direction and parallel and collinear. In this case, both Zi, comma Zi minus 1 are collinear. In this case, you can choose the origin to be at any point along this. Okay, any convenient point, you can locate the origin wherever you like along this line. Along the axis. Okay. So this is step 2, which is origin, which is set up the origin. Okay. Once you have done that, the next thing is to set up the x-axis, right? We have finished the origin. The next step is to set up the x-axis. So to set up the x-axis, what we'll do is,
Professor, what was the original drawing for B?
I'm sorry,
What was the original drawing for B?
what was the original drawing for
B.
B? This one. The original drawing was this. The two axes are parallel like this, Zi minus 1 and Zi, let's say. Right? They are parallel. So you want to find out where the origin might lie. So in this case, you'll draw a parallel perpendicular to both these axes. It can be in this direction or it can be in this direction. Eventually, you will locate it at the intersection of GI and the normal. So this will be OI. Okay. So you can draw a parallel line along this. Now, for all these cases, I might have to draw this again. For all these cases, the x-axis will change, right? The x-axis will change depending upon what scenario we are talking about. So let's say that, let's go to step 3, which is set up the x-axis. Okay, now if you have a manipulator structure, we have to make sure that the transform we get, the homogeneous transform we get, is unique, right? The table might not be unique. For example, depending upon how you set up the axis, you might get a different table. But eventually, when you do the transformation, the homogeneous transform, it has to be unique. To make sure that there is a uniqueness, otherwise we'll end up with different transforms for the same structure, which can be, which will lead you to 2 points for a given joint displacement. What we'll do is, we have 2 rules, right, that we have to mention, always keep in mind. 2 rules that guarantee the uniqueness of the DH transform, okay? The first one is, xi should intersect zi minus 1. Okay, xi should intersect zi minus 1. And the second rule is xi should be perpendicular to both zi minus 1 and 0. If these 2 rules are not satisfied, then your DH table is completely wrong. Okay? It's not unique, it makes no sense to have this. These 2 rules, DH1 and DH2, guarantee the uniqueness of the DH transform. Okay, the table is not unique. DH table is not unique. You can come up with 2 different tables. All right, DH table is not unique, but the DH transform is unique. Okay, so 2 things that you always have to keep in mind, that xi will intersect the previous axis, and xi is perpendicular to the 2 z axis. Let's write that down so I can have some board space.
To bring that one down. To bring that one down.
No, that's cover this, right? So I cannot use it.
What's the DH table?
DH table is the same thing. Can I have it having good, right? You said this is DH, right? We drew a table here, right? With 3 rows, okay? DH table or DH notation is the same thing, all right? When you drew the table that was explaining the manipulator like this, A alpha D theta, that's the table. Okay. All right, let's take the first case here, right? In which case, Zi and Zi minus 1 are perpendicular. Now in this case, how will you draw x? And this is the, let's say this is O, right? Let's say this is OI. Let's say this is OI. How will we draw x? X has to be perpendicular to both of these. So there are 2 ways to draw x. X can be within the board like this, or it could be coming out of it. Okay. All right, you have two options for x. You can either take it within the board because it has to be perpendicular to both these axes and also intersect this. So it can be within the board or it could be outside the board, in this case A. Right, in the first case where Zi is perpendicular to Zi minus 1. Here obviously we have drawn it, the common normal is already there. So you have Zi minus 1 and this is Zi. Okay. Here you'll have either you can draw x like this, xi, this is your origin, oi, or you can also draw xi like this. Okay. You have a choice of drawing xi in either direction, like this or like so. Finally, we have the collinear case where both of them are in a straight line. This is Zi minus 1. How about here?
Two different.
You can have infinite positions, right? You have this and you can have a perpendicular that goes around, right? You can have infinite positions for x. There is no correct way you can, let's say you fix the origin here, oi. Obviously, even origin is up to you. You can find it at any convenient point along the line, right? So let's say you fixed oi here, your xi can be like this, it can be like this, so long as it is perpendicular to both, right? You can have it in a disk around it, anywhere along a disk that is perpendicular to it.
But it has to be on Zi.
It has to be on,
Zi.
it has to be through the origin. The origin is already lying on that axis, right? So it has to intersect Zi minus 1 and be perpendicular to both Zi and Zi minus 1. So intersect Zi minus 1. If you look at all of the cases, does xi intersect Zi minus 1? Yes. It intersects Zi minus 1, it intersects Zi minus 1. Is it perpendicular to both? Yes. In this case, it's either within the board or outside the board. Same thing here, it's either in this direction, or here. So it does not matter. Some cases you'll have the axis like this, Zi is like this, Zi minus 1 is like this. It's the same case, it's anti-parallel, so this case applies. Or here you might have it like this, collinear, but opposite. Okay, so once the x-axis is fixed, that's final, right? The last thing that we do is we add a frame, add the end effector frame. So step 4 is add the end effector frame. Okay, so the end effector frame, what I'll do is I'll just replicate this, but let's finish drawing the x in this case. So here if you look, the first origin is fixed. This is the global frame of reference, x dot and y naught. Now I have to draw the x here. In this case, these two are perpendicular, so I'll draw x along a line that is perpendicular to both, a common normal. A common normal is like this, so this will be x1. Okay, so this is x1. Now what I'll do is I'll finalize the frame exactly the same as the last frame. So my end effector frame will be like this. Okay. This is my end effector frame or the final frame. Alright. So if there is a n degree of freedom manipulator, if you have an n DOF manipulator, the number of frames will be n plus 1. Because you start from origin and you go up till n. So 0, 1, 2. This is only a 2 degree of freedom manipulator. The first frame is the reference frame, the global reference frame, and you end up till the end effector frame. So you have n plus 1 frames in the case of a n degree manipulator. Alright, so now we have set up all that we need. It's only a matter of measurement. Now in this case, there are two angles. The angles are really important. The distances are very fairly easy to measure, so it's not a big deal measuring A and D. The angles are a little tricky. So when you look at the original diagram I gave you, when you look at angle theta, theta is the angle measured between xi and xi minus 1, xi to xi minus 1 along zi minus 1. This is theta. You measure it about zi minus 1 from xi minus 1 to xi, like this. Okay? This is theta. Alpha is the angle between zi minus 1 and zi measured about xi. Okay. Alpha is the angle between zi minus 1 and zi measured about xi. Alright. The distances are simple. A you measure along xi. Distance A is measured along xi, and D measured along Ci minus 1. Okay. As we do more examples, this will get a little more clear. But until now, the first thing is setting up the frames. We start with setting up the Z, which is very easy, perpendicular to the axis of rotation or along the axis. Locate the origin, set up the x-axis. Okay. Now the first thing that you do is, because these are two revolute joints, we'll write this as θ1 because we know this is going to be variable. Okay. These two are variable parameters, so I'm just going to put them as asterisks. Okay. Everything else in this table is going to be constant. Okay, let's start with A. How do we measure A? A is measured, A1 in this case, this is link 1, link 2. Okay, so A is measured along x1. You measure x1 from here until you go to the previous origin. So from here until it intersects